For this video, we're going to be talking about specific heat. Well, what is specific heat? It is like the energy required to raise up 1 degree Celsius for 1 kilogram of mass. Okay, so its specific heat would be different for different substance. Like for example, I have 1 kilogram of iron versus 1 kilogram water, and I'm going to raise up the same degree, 10 degrees Celsius. Iron only require 4.5 kilojoule, and however water require 41.8 kilojoules. So you can see it takes different amount of energy to raise the temperature of different substance by the same amount. Then, so what is specific heat again? It's the energy required to raise the temperature of a unit mass, which is 1 kilogram, by 1 degree. Okay. So specific heat gonna have a unit as kilojoule, the heat required to raise up 1 kilogram of mass per kilogram for 1 degree increase per degree Celsius. Okay. And specific heat can be classified as CV, which means that constant volume versus constant pressure, CP. So the energy required to raise the temperature of unit mass by 1 degree when volume is constant, that's going to be CV. When the pressure is constant, it's going to be CP. So let's look at this cartoon here. This is a constant volume, obvious, and this is going to be a constant pressure. And think about the heat required to raise up this 1 kilogram of mass, 1 degree Celsius. Which one requires more energy? Which one requires more heat? So obviously this one with a constant pressure will require more heat. This is 5.19 kilojoule versus 3.12. Why is that? Think about it. They all only going to achieve the same goal to raise up 1 degree Celsius. However, for constant pressure process, since this pressure has to be constant, what do you think? The piston gonna keep on being lifted up, right? So it's gonna be keep the pressure to be the same. Otherwise, pressure gonna increase. In order to keep this pressure constant, the piston has been moved up. Where's that energy coming from? What energy is used to move up the piston? It's gonna be extra energy required for that. So that's why if you want to keep the constant pressure process, the required energy is going to be more than constant volume. So here we made a conclusion. CP is always going to be greater than CV. Okay, CP is greater than CV. So here's the definition for specific heat. CV is going to be the energy required over for 1 kilogram mass per 1 degree for constant volume. But now let's think about it. For constant volume process, for first law, we're talking about heat transfer Q is equal to delta U, right? So that heat transfer Q is going to be partial U, and here small u, which means it's already divided by mass, so it's just partial U over partial T. Then, however, for constant pressure process, the heat required, the energy required, think about first law for constant pressure equation. Heat transfer is equal to delta H plus work others. There's no work others, so therefore the heat transfer Q will be just equal to delta H, and then divided by mass, so you get the small h, and then per degree Celsius partial T. So that's going to be the definition of CV and CP. CV is a change in internal energy. Now we understand why here we're using U, and here CP, why we are using H here. Okay. So that's the formal definition of CP and CV. Now let's thinking about it. The unit for specific heat, CP or CV, it's going to be kilojoule per kilogram per Kelvin for degree Celsius. Can I change that Kelvin to degree Celsius? Are those units identical? If you say yes, you are correct. Why? because this is a change in temperature. They are changing it for 1 degree, increased by 1 degree Celsius. 1 degree Celsius change is going to be equal to 1 degree Kelvin change. Therefore, degree Celsius and the Kelvin here can be exchanged. It's exchangeable. All right. So, this slide is talking about the heat capacity is not a constant. However, it actually varies with the temperature. The higher temperature it gets, then the specific heat is gonna be higher. So it's proportional. It changes with the temperature. Why is that? Think about if you have the same amount of air, 1 kilogram, you all want to increase the 1 degree Kelvin. Here it starts at 300, however, it starts 1000. I mean, when you already have a higher temperature like 1000 Kelvin, then you want to raise up 1 more Kelvin. You know it's getting harder and harder, so you're going to require more heat. Therefore, specific heat at a higher temperature is going to be higher because the heat required to raise up to 1 degree Celsius is greater. All right, that specific heat, it changes with the temperature. Okay, and we talked about earlier, Cp is always greater than Cv, so that statement is true. And here I want to focus on this equation here. And we talk about Cv and Cp, it is a function of a temperature. At different temperature, higher temperature, you're going to have a higher specific heat. And the same thing apply for ideal gas here. If it's ideal gas, internal energy U and enthalpy, they're going to be increased with the temperature as well. Okay, for ideal gas, U, H, Cv, and Cp, they varies with temperature only. Now let's look at the equation we have over here. We're talking about Cv is partial U over partial T, so we can write du as Cv T dt. Cp, we said it's partial H over partial T, so we can write dH equal to Cp T dt. And when you are going to integrate those two, so delta U is equal to Cv dt integral, and delta H is going to be equal to Cpt dt. That's going to be our two equation here. Now, very last concept I want to cover is going to be the relationship between Cp and Cv for ideal gas. Okay, this is for ideal gas. We know Cp is greater than Cv, but how much greater? Then here we can derive it. We start with the enthalpy equation, H equal to U plus PV, and then we're going to work on dH is equal to du, and the PV equal to RT. That's the ideal gas equation. And the dH is Cp dt, and we talk about du is Cv dt. And put it in there and take R out, being a constant. Now let's take a look at it. You rid of dt on both sides equation, then here's a relationship. Cp is greater than Cv. How much greater? Gas constant R. Is that something? So now you remember Cp is equal to Cv plus R. All right, so another small concept is called K. K is specific heat ratio. Basically, it's Cp over Cv. So K we're always going to be greater than 1. Consider Cp is greater than Cv. Therefore, K is going to be greater than 1, right? So that's all the concept for specific heat. If I were trying to write it down, the major ones, I will be having this. I will say Cp is greater than Cv, and for ideal gas, Cp is equal to Cv plus R, and Cp and Cv gonna have a unit of kilojoule per kilogram per Kelvin, because that's heat required to raise up 1 degree Celsius and for 1 kilogram mass, and that's gonna be same as kilojoule per degree Celsius. Why so? Because that's delta T. Degree Celsius change equal to delta T in Kelvin. Okay. Then another thing I want to talking about is K, specific heat ratio. That's going to be the ratio between Cp over Cv. That's going to be greater than 1. Another concept is basically the formal equation for Cp and Cv. Essentially, they give us du is equal to, here it's Cv dt, and dH, the enthalpy, is equal to Cp dt. All right, so that's what we have so far. And then we're talking about, if you want to find a delta U, it's going to be Cv dt, and delta H is going to be Cp dt. Another concept to quick recap is for ideal gas. This U, H, Cp, Cv, they are all function of a temperature. So in other words, when temperature increases, U, H, Cp, Cv, they increases, right? So I'm gonna give you one quick example. If it is isothermal process, isothermal, we know it's gonna be what? Constant temperature. If it's constant temperature, what do we have for delta U for ideal gas? And how about delta H? What do you think? Remember, ideal gas is a function of temperature only. So if temperature is the same, what do you think about the change in energy, internal energy and enthalpy? That's right, equal to 0. So that's something quick we can conclude for isothermal process. For ideal gas, the internal energy and the enthalpy change will be 0. So that's all. So that's a quick recap on specific heat, and I'll see you next time. Bye.